go outside in some reason. Okay.
Voltage or adjust the firing angle to your precision, you may use both the gates. So it is two terminals, anode and cathode. There are two gates, anode gate and cathode gate. So we call it silicon control rectifier. Thermistor, only one gate will be used, not both the gates. And your PNP diode, we consider that no gate is used, no gate voltage is applied for our discussion. But anyway, that is not going to be the limitation. All the things are just merged in one, and that we call it negative resistance device. So let me see, I'll just summarize the things in few lectures. I think some students are joined by now, so they can convey their notes to their friends. I think I'm not getting that handler for presentation, Professor Gupta.
Okay, sir, I am giving. Wait, please wait.
Now
So
it has
now
come.
it is coming.
Now it has come. Yes.
Okay.
Okay. I describe PN as combination of two transistors. This is your P, this is your N, this is your P. You can say the whole material is P, this is your N. So that way, here is the input, here is the output. So that way I describe and made a transistor structure like that. This becomes PNP transistor, this becomes N here, this becomes NPN transistor. So there I describe your current flowing through this. This is my I. Okay. Some voltage is applied here. And this current I is coming like that. This is my current I. So this current I by collector and base, that splitting in the, you can say, coupling of the PNP and NPN transistor, I explained this current I was coming as ICO2. That means 2 I have taken, which transistor? NPN transistor I am taking as transistor number 2, PNP I am taking as transistor number 1. Here is your ICO1. In the book it is written minus ICO1, so should not confuse, because they have taken the convention like that. For this current, only the convention it is chosen over there. Here is 1 minus alpha 1 for the PNP transistor, alpha 2 for the NPN. If you want, you can put it your alpha N, you can say as alpha P. That way you can say these are the two transistors like that. Suppose I take ICO2 minus ICO1 and the two reverse saturation currents are the same. It will become 0 in the numerator. That means no current is flowing, but that is not the case. So don't confuse, it is ICO1 plus ICO2. These joint flow of the two reverse saturation currents. In both the cases, the respective base lead is open. Sorry, respective emitter lead is considered open. Here also corresponding emitter lead is open. So that way these currents are measured, that is evaluated, 1 minus coming like that. Then I said, instead of individual alpha 1 and alpha 2, if alpha 1 plus alpha 2 becomes your 1, then what happens? Denominator becomes 0 and this current becomes infinite. So it is your some kind of your unstable state. So it is not the case actually. Alpha 1 plus alpha 2, very high current will flow. And when the high current flows, what happens? There is one junction, I call it my P1, PN junction. I call it my J1. There is another junction, another junction is coming here. First junction was here. Another junction, this junction I call it J2. And this is your NP, this is your P, this is your N. So this is my J3. So when alpha 1 plus alpha 2 becomes your 1, coming close to 1, then what happens? High current flows, and this one, this is reverse bias. J2 is reverse bias. J1 is forward bias. Initially, J3 is also forward bias. So when heavy current flows, this forward bias is as such no problem. It will be working fine. Now this one will go to some kind of breakover region. I cannot say breakdown, that will damage it. It is going to break down actually, junction is going to break down, but is for the device it is breakover region, breakover. So this J2, in this case, J2 becomes breakover. And high current flows. When high current flows through it, okay, then what happens? Alpha 1 plus alpha 2 becomes larger than 1. Plus alpha 2 becomes larger than 1. This implies reversal of the current because denominator becomes negative. So this is alpha 2 of course here. Okay, reversal. So current is reversed. So at that time what happens? I'm just repeating the same thing. At that time what happens? Your J1 is reverse bias because current is flowing from right to left. Your J3 is also reverse bias. So current flowing through these two junctions is very small. But what about your J2? Current has reverse. So this becomes a forward bias. So drop across the central junction is now very small. But at the two outer junction drop increases. As a result, what happens? Current is becoming more reverse bias. Current is reverse current I'm talking. Reverse current decreases. See, when it became alpha or alpha 2 slightly greater than 1, reverse current was also very high. So because of reverse bias conditions becoming stronger and stronger, current is decreasing. As a result, alpha 1 and alpha 2 decrease. When alpha 1 plus alpha 2 become less than 1, Forward current flows. Forward current flows. Okay. Now here you see this has given me stability of alpha 1 plus alpha 2. It will be fluctuating near 1, but it will not become equal to 1. That will be very momentary case. Device will not be damaged. Where is the negative resistance coming then? Negative resistance comes here. Alpha 1 plus alpha 2 becomes your 1. Very high current flows. This has gone in breakdown region. So voltage drop across this is now reduced. In the breakdown region, current will be increasing because this resistance suffered by this becomes very small. Here also, across this junction, the drop is reduced. Here also drop is reduced. So voltage drop from this end to this end across the device. Voltage drop across the device decreases, whereas the current increases. The resistance is V by I. Current in the device increases. So V by I. V by I becomes what? Current increases, voltage decreases, delta V by delta I becomes negative. So this implies delta VD by delta ID is negative. I can say less than 0. Less than 0 or what? Delta V VD less than 0. You are right. So that way it is having the negative resistance and the stability of alpha 1 plus alpha 2 around this 1, that is guaranteed. It is not going beyond that. So a device is not going to this kind of your state where it gets fused. No, that is not taking place. Because alpha and alpha 2, when it decreases, okay, it brings the current once again to the limiting value, and that is a operation. Could I explain the things again? Okay, so there is no question. I move to the second part because here I explain once again what is the meaning of the gate. If I put a gate here, this is your gate is your anode gate because at P we call it as anode. If I am putting a gate here, this will be your cathode gate. And cathode gate voltages in SCR, silicon control rectifier, helps us in controlling the firing voltage. What this voltage will make this device on. That means I becomes very high. What voltage will make this device off? That means these two become your reverse bias. So with this voltage, applied voltage, it will become on and off. And from the diagram I explained, if you remember, it was coming something like that. So I bias it here. When the positive trigger is applied, I have come to this point. So it will go to this current I. This is my voltage. After that, it will return back to this because trigger is gone. It will return back to this. This is also returning back up to this point. But it cannot come below that because this is the stable state remaining there. So remaining at the same voltage where it was biased. A negative trigger will make this voltage to somewhere here. So here it comes to this point. In between there is no other point, valid point for us to measure a record. So it has come to this point. That means this voltage. And this voltage will once again, trigger is gone, you return to this. So this voltage of the device remains the same here and here, and you can go to two stable states according to this kind of your negative resistance. Negative means it's jumping from here to here all of a sudden. This is fraction of milliseconds or so I cannot observe what is happening in this direction. So V and I characteristic is changing according to that. So it is used as a switch. So thyristor is used as a control switch in your power system. Okay. Now there is something known as uni-junction transistor. It is also having a negative resistance. Uni-junction, single junction, but we call it a transistor because there are three terminals in that. Uni-junction. Transistor. It is not a diode. That means three terminals should behave like a three independent terminals of the BJT or FET, whatever you have learned. So it is uni-junction transistor. This will exhibit the negative resistance property. Okay. What is that? Here you are taking, it is made of silicon. Okay. So we take N-type silicon bar. So we are taking N-type silicon bar, okay, and you have made here ohmic contact. Ohmic contact. Here also it is ohmic contact. So silicon bar is having simple resistance here. It is having simple resistance here. This is ohmic contact. Then you take aluminum wire. I am putting aluminum wire like this kind of shape. Okay. This is aluminum wire is now fused here. Just see. Here is ohmic contact, but if I fuse the aluminum wire, N-type silicon, if it is highly doped, okay, for that aluminum becomes something like P-type. Aluminum, the doping will be small. So N-type is heavily doped. It becomes likely doped P-type material at this point. So it becomes a PN junction. So aluminum is not ohmic contact, but here even these are wires only, but they are ohmic contact. They are not fused. They are just made a contact there. So ohmic contact, here it is fused, so it becomes your PN junction at this point. So what we call here, we name this as my emitter. This I can say as my one base 1 or base 2, whatever name you give. Okay. Let us say base 1, I'm calling this as my base 2. So there are two bases and one emitter. So there is nothing like any collector. That concept is not there. So when we make this one for use, okay, we take base B1 towards common point. Common emitter you have learned there. So this B1 will be connected to the common point or earth, your ground, like that for the device, and base B2 will be kept here for the bias case or so. Okay, so B1 and B2 will be going there. Below means it's going to the ground, here it means going to the supply, like that. So the supply characteristics I'm not right now interested. This we represent like that. So we call it as my emitter E. So from the emitter E, the current will enter in the forward bias case. It will pass to this through this base B1, and here there will be a supply voltage. Like that. There has to be a voltage here. I call that voltage as my VE. So VE will be given as a bias, as given as a trigger, whatever name you give. With respect to VE will be plotting the voltage. Which voltage? This voltage between B1 and B2. This we call it VVV. So in the characterization, we plot like that. This is my VVV. And this one will be my VVB and current IB1. So VVB and IB1, IB2 I'm not considering because IB1 will be equal to IE plus IB2. So in IB1, IB2 is already incorporated, considered in that. So I will be doing the analysis with respect to IE and IB1 by changing the voltage VVB. So it will be exhibiting a negative resistance. We'll try to see how does it give that negative resistance. Any question here right now before we start for the characterization? Any question? I welcome. No. Okay, Professor Gupta, should I proceed now? Students, did they convey to you?
Sir.
It's okay now? You also take the feedback that if they are not saying something, what should I understand? Should I apply my own wisdom to go for the review or repetition or something? But they should ask. I think what harms them? If they ask something, I think they.
Students, please keep on asking questions. Otherwise, it will be
because conceptual thing, I can talk this entire Pdss subject in 1 hour. In seminars, etc. When invited talk, we give hardly take 45 minutes to complete this kind of lectures. So switch and all that. On switch, simple switch, we cannot take more than 45 minutes or so. It is subject also for that. So we are going for all kinds of your discussion kind of opening I'm giving from time to time. You avail that. Otherwise, for me, just talking doesn't make any advantageous position unless it is of Huge.
So, feels like who are there.
Okay, now I'm going to the analysis. You prepare your question. I have given n type
Sasank,
material. Yeah.
Sasank,
It's
are you
okay.
present?
Yes, sir. Yes, sir.
Okay, fine.
You ask anything, any question.
Anything comes to your mind, because this uni junction transistor, I don't think it is taught to you in your first year and second year devices class. If it is taught, it's very nice. Otherwise, UJT is also a kind of negative resistance device. It is very frequently used in other, I mean, circuit designs, which I explained in the very first day. What is the importance of negative resistance device? Okay, by taking a simple diagram, your RC low pass diagram, parallel to that C, this negative resistance was coming. What way it was helping in the switching time reduction or so. I'm coming to the analysis now. Okay. Voltage between B1 and B2, I call it VVB. Voltage between B1 or B2 and B1 and B1 is, say, VBB. Okay. So similarly, a resistance of device between B2 and B1, I can say as RBB, which is nothing but ohmic contract RB2 plus RB1. Okay, it's not like parallel combination. Two ohmic contacts coming in series, so RBB is like that. So what is my VB1? Because B1 is going to the ground through some resistance, biasing and all that. So VB1 would be how much? You already know the potential divided circuit. RB1 by, I'm quietly calling it RBB, that this series combination of that into VBB. Okay, now I am putting a bias, putting a trigger at VE now. Okay, first of all, let us see what way the bias is helping there. One condition is VE less than VB1. Another is VE equal to VB1. And third one is VE greater than VB1. In the three cases, what is going to happen? If it is this less than VB1, so that means the emitter and B1 junction, this PN junction, is reverse biased because aluminum is P type and silicon rod is your N type, so reverse bias. Okay, so here what happens? How much current will be flowing through the junction? IE equal to 0. No IE will be there. IE becomes 0. And how much current is flowing through the device? VBB by RBB. Okay? VBB divided by RBB is the current flowing through the device. Now when this becomes VE becomes equal to VB1. Okay. So here, sorry, Y0, I negative, reverse bias case, side E negative. Here becomes IE becomes your 0. It is in fact less than 0, so negative. Here becomes your IE equal to 0. When VE is greater than VB1, IE becomes greater than 0. It is forward bias. Junction is forward bias. Here the junction is reverse biased. Okay. So here current is not flowing like that. So when IE becomes forward bias, your junction becomes forward bias, IE becomes greater than 0. So high current from emitter to B1 is flowing. So this will lead to, okay, reduction of BB1. BB1 is very small. When IE becomes greater than 0, VB1 becomes very small. And VB1 formula I have written here, RB1 divided by RBB into VBB. Okay? So that we have to see VB1 has reduced. As a result, what is the current flowing through the device? IBB, you can say, this current. When VB1 becomes very small, okay, IB in the device current, that current will increase. Why? Because IB1 equal to IE plus IB2. When this becomes very large, countably infinite, then IB2 will become 0. When this becomes countably infinite, IB1 becomes very large, this IB2 becomes 0, and IB1 will be equal to my IE. That will be dominating. This ohmic contact will have the same amount of drop, that is not going to change. So that way. So if it is IB1 becomes large, IB2 becomes 0. So the current in the device is reducing. Is reducing or increasing? IB2 becomes 0. Once again, IB1 is increasing, IB2 is decreasing, and VB1 is becoming small. Okay. If VB1 is becoming small, that means RB1 is reducing. Okay, sorry. Let me write here this way. VB1 reduces, then RB1 increases. VB1 is, sorry, RB1 is also reducing, sorry. VB1 reduces, RB1 also reduces. I have to take fresh page. If this is reducing, this is also reducing. VB1 reducing, RB1 is reducing. When RB1 is reducing, here, this one. One second, when I'm making the mistake. Okay, fine. Now, I think I'll take a fresh page. Yeah. Here, what we have seen that IE is greater than 0. That means it's forward current, forward bias current. Okay, across the junction. This implies that VB1 decreases. And at the same time, RB1 also decreases. So RB1 decreases. Okay, fine. Okay, decreases. So here what happens? If RB1 is decreasing, then current through RB1 increases. If resistance is decreasing, the current is through the low resistance is higher. So current through RB1 is increasing. So remember, my IB2 becomes approximately equal to 0 when saturation is achieved. Saturation is achieved. Okay, because IB1, IB2 I'm saying, IB1 equal to IB2 plus IE. Okay, so when IE is increases, to IB1 becomes our very high, countably infinite. That will be equal to my IE, that is the forward current. So this IB2 will be tending to 0. If IB1 is tending to infinity, tending to 0, IE will be same thing as my IB1. So across the device, my voltage is VB1, which is decreasing. So delta VB1 is, if it is decreasing, okay, the current is increasing. Here it is decreasing, the current is increasing. As a result, negative resistance is realized. For VB1, okay, and IB1, these two, IB1 is nothing but your IE. Suppose you plot VB1 and IB. So this plot is something VB1 and this is my IB1. Because IB2 becomes close to 0. So here VB1 comes like that, very low value of current IB1 is there, then it becomes like that, it goes like this. So this is my UJT, unijunction transistor characteristic. So using UJT also, single junction gives me negative resistance, and that you can use for your switching action, or you can use it for anything. Here again in this particular region, you are not able to do any kind of measurement. From here, in fraction of milliseconds or so, it comes over here. So like that, this is the device. So this, I have completed UJT today. Any question is there related to UJT, or you will be able to read yourself from the book. It is given in the book also. I have summarized from the book by Millman and Taub. I think all of you are having that book. Anybody who is not having that book? Pulse Digital and Switching System by Millman and Taub. Anybody who is not having? Professor Sen Gupta can mail the link in that case if they are not having. Anybody who is not having that book? All these are taken from that book. Your syllabus is resembling with that book. Course, whatever content is there, your content is resembling with that. Okay, coming to the one which you already know. Tunnel diode. How many of you are, anybody who is not knowing about tunnel diode? Tunnel diode, please. Unless you reply, it will just talking in just in air. That is of no use in that case. Tunnel diode is something different than Zener diode and something different than your ordinary diode. Its characteristic comes like that. Why it is coming? This is my V, this is my I. If I'm changing my V, my current I is increasing like this. It is a voltage operated device. That's what I'm saying. So here voltage is changing, current is changing. After that, it starts falling. Now voltage further increased, it goes like that. This is a nonlinear portion. It goes like that. VI characteristic for tunnel diode comes like that. May I know how does it happen? Can I measure this portion? IV characteristic this portion? Yes, I can measure because I'm changing my voltage. I'm measuring my current. Okay, so this is your PN junction. So voltage is this voltage, positive voltage at P terminal I am applying, and other portion negative is going to ground, that will be there. So voltage positive we are applied to P terminal, forward voltage applied. When I go for the reverse bias case, here it is a straight line, just see, it is different than all other things. So why it is happening? In tunnel diode, why it is happening? Anybody who knows this answer? I think this your teacher must have taught to you. It is like that your semiconductor is having bands like that. One is called conduction band CB. This is the valence band VB. When it is intrinsic semiconductor, its Fermi level lies in the center. Intrinsic semiconductor. Okay. When I make it P type, I have doped some group 3 elements in that, because semiconductor silicon germanium is group 4 element. So I have added group 3 element doped inside that. So this becomes my CB. This becomes my VB. And Fermi level, now because number of holes have increased, so it will come closer to the valence band. This is your P type. If doping is increased, it goes further down. It may come inside the valence band, because other energy bands will remain unoccupied. Similarly, when I go for the N type, I am doping group 7, group 6 elements, group 5 elements in that. So this is my CB, this is my valence band VB. Fermi level comes closer, because here I have doped some majority of electrons. So here this is occupied by electrons and this is occupied by holes, which are hypothetical particles. So holes is positive, this is my electrons. So more electrons are put, Fermi level, this is energy level, which has got the probability of getting occupied as half. Probability of getting occupied becomes half, so it will shift to the conduction band. If in N type, it will shift to the valence band if it is P type. Now when I make a PN junction, okay, by fusing the two together, the Fermi level should come in line, in one line. As a result, this will apparently going down in the energy level, this is going apparently up in the energy level. So your connection becomes something like that, and transition takes place something like this. Here is my Fermi level. It is going in a straight line, because probably that energy level in the PN junction device, which is occupied 50% of the time, which is Fermi level. Okay, it goes like that. So this is my P type, this is my N type, and my doping is increasing, P type will go up, N type will go down, Fermi level will go inside the valence band of the P type, it will go in the conduction band of the N type. Okay, and that is the particular point where Zener diode has come. And further, if doping is increased, it will lie below the valence band of P type, at the bottom of the P type, and it will lie at the top of the conduction band of the N type. Bottom of the valence band of P type, top of the conduction band of N type, there it will be touching. That will be your tunnel diode. I will explain that. And this negative resistance we are not using for the switch. Remember, because this portion is not taking place very swiftly in fraction of millisecond or so. Because here gradually the way the voltage is increasing, this current is decreasing, and I can see this characteristic by laboratory experiment. So this we are not using as a switch, it is used for other purposes. But this is giving negative resistance. This is your negative resistance region, NR region. Negative resistance region. Delta V, because V is decreasing, divided by delta, V is increasing, divided by delta I, because I is decreasing. So it becomes your negative. So this is the portion it is coming. So I will just talk about tunnel diode in the next class. How does it give this characteristic? And if you want to use it as a two stable states, of course this state is something, it is also there. We have to come to this stable state in the negative resistance also. But how to make use of this state and this state? Once I am here, another time I am here. This is voltage control, so current will be having two different values. Once this current is there, another time this current is there. These two currents are, here current is remaining the same, but voltage will be changing here. So it is a voltage operator, that way I will explain to it in the next class. Okay, so should I close it here? Friends?
Yes.
Okay. Position Gupta?
Yes, sir.
It's okay for them? I think
Yes, yes.
they are not asking conceptual subject answer is interactive. I'm just talking on my own. Tunnel diode, etc. They have read it, but
yes, they are listening, and also if it is physical mode, then it will be better. It is not physical mode, so yeah, they are managing.
physical notes is there in the book, this Millman top book. Tunnel
Yes,
diode is not explained there. Tunnel diode is not explained in that. Millman Halkias integrated electronics
yes.
talked something like that, but not exactly in the way I have.
Tunnel diode is given in Streetman, book of Streetman.
That way, because Millman Halkias also has not described tunnel diode. General diode it has described, and after that it has gone to other discussions, not for tunnel diode. So tunnel diode, they had just given the characteristic and started explaining that. Anyway, I will do that device characteristics also, and
Yes.
for their say continuity. But there they have to make the note. What way when I am speaking tunnel diode, I think other things are already available in the book. So I have given summarized form of the presentation. Details they can see in the book. I put the questions to me if they get some difficulty or so. Okay?
Okay.
Okay, friends. So good day. See you again. Wish you happy Holi because you are meeting on Monday. Next Thursday is a holiday. Friday is a holiday. So I wish happy Holi to all the students. Okay. Happy Holi to all students and happy Holi to you also, Hussain Gupta. Of course, you can meet tomorrow.
Same to you, sir. Same to you.
Thank you. Thank you. Fine. Good day.